so let's get started here. Before we jump into discussing alkynes, right, our current chapter, there's one sort of slide that I want to bring up that we had talked about at the beginning of last week. And I think when we talked about this, it wasn't clear that this pertains to all of our stereospecific reactions, right? So we talked about this, when do I need to worry about stereochemistry cheat sheet here? And we built this for our halogenation reactions, right? Well, this is also true for all of our stereospecific reactions. All of our syn addition, anti-addition reactions that we talked about, you'll use this same scheme in terms of when you're going to need to worry about your stereochemistry. So we talked about it with regard to our halogenation reactions. It also applies to those syn addition hydration reactions. It applies to our syn and anti-addition diol reactions, right? This same scheme here works for all of our addition reactions that are stereospecific. So please just make note of this page here and how it's going to help you figure out when you need to include your dashes and wedges and when you don't, all right? Cool. All right, so going back to alkynes, okay. Remember we talked about how alkynes, just like alkenes, they also undergo addition reactions because they also have those pi bonds, right? We used our hydrogenation reactions as an example here. We take our alkyne and we do an addition reaction, adding to that carbon-carbon, in this case, triple bond. But what we produce on the other end is now an alkene. It still has yet another pi bond. So then we can do yet another round of our addition reaction, right? So that's the big difference here between our alkenes and our alkynes. They both undergo the same types of reactions, but alkynes have 2 pi bonds instead of 1, all right? With regard to hydrogenation reactions in particular, we had these 3 different catalysts that we can use, and we'd get a different result depending on which one. If we used our hydrogen and palladium or platinum, what we were introduced to in the previous chapter, this works on alkynes as well as alkenes, right? That's when we learned about this method here. And so these are a really strong hydrogenation method, which will fully reduce that alkyne to an alkane. So if we want to stop at this intermediate step here, we had to use these 2 special catalysts, what's called Lindlar's catalyst, and then our sodium or lithium in ammonia. All right. Lindlar's catalyst will produce an alkene, but specifically with that Z stereochemistry. Our sodium and lithium here, sodium or lithium in our liquid ammonia will specifically produce the E catalyst. There's one more thing that I forgot that we're going to need to add to our notes for this particular reduction method here, our sodium and lithium in ammonia method. All right. What we want to note here is that this produces this E stereoisomer, but importantly, it does not work for terminal alkynes rather. All right, a terminal alkyne is when that carbon-carbon triple bond is located on the very end of our molecule, meaning that there's necessarily a hydrogen here, as opposed to if that carbon-carbon triple bond was in the middle of our molecule. This would be called not a terminal alkyne, but an internal alkyne. All right, and we make this distinction. It's helpful for a few reasons. All right, importantly, first of all, what we're seeing here, the fact that one of these will work just fine for these reactions, our internal alkynes. It will not work for our terminal alkynes when they're located at the end of our molecule. Right, so this is when our carbon-carbon triple bond is at the end of our molecule. So just to kind of start here to practice and compare and contrast these reactions, I want everybody to take a second and fill out this reaction wheel here for our carbon-carbon triple bond, our propyne here. right, so we're starting with our alkyne, our carbon-carbon triple bond. If we were to use hydrogen gas and palladium, what would be our functional group of our product? Alkane. All right, so we should now have a 3-carbon alkane. If we use Lindlar's catalyst, this allows us to convert our alkyne to an alkene, specifically with that Z stereochemistry, although here, because it's located at the very end of our molecule, stereochemistry doesn't even matter. All right, and then like we said, what's going to be our product here? Alkane, alkene, or trick question? We cannot use a terminal alkyne for this method, so we would not get a product here for this method. All right, again, we're just going to note, so it's clear in our notes why, because this is a terminal alkyne. Cool. So these are one of these addition reactions that we saw some overlap between our alkenes and alkynes. We talked about halogenation reactions and hydrohalogenation reactions. There's one other addition reaction that we're going to cover that has some overlap between these two, and those are what are called hydration reactions. And in a hydration reaction, what am I adding here? This is the addition of what to our pi bond? Water. All right. And we're going to see two similar reactions to what we saw before in our hydration reactions. We can do an oxymercuration of our alkyne. All right, so let's get a sample alkyne here to use. Okay, so we can do our oxymercuration reaction. We saw those with alkenes. We also saw with alkenes our hydroboronation reaction. All right, so we're going to start with this same alkyne for both of these here to illustrate the difference. Okay, let's take a look at our reagents here. What you'll notice is that they're not the exact same, but they still have that same key player here. Instead of using mercury acetate for an oxymercuration of an alkyne, we use mercury sulfate in dilute sulfuric acid. And in our hydroboronation reaction, instead of using straight up borane, we use a poison version of borane, which has these two alkyl groups on there. And then we have our same second step here with our basic hydrogen peroxide. All right, now remember, what we said is we don't have to memorize these reagents. We want to identify these key things here. And just like before in our oxymercuration reaction, we see that mercury metal, something we don't see very often in organic chemistry. Likewise, for our hydroboronation, we see that boron that we're not used to seeing in organic chemistry. So again, just key thing out of this big ugly list here, what can my eyes gravitate to that's going to help me remember what this reaction is? We have mercury for an oxymercuration reaction, just like we saw for alkenes. And we have boron for a hydroboronation reaction, just like we saw with alkenes. All right. Now, also similar to alkenes here, there was this regiospecificity of these two reactions. One of them was Markovnikov, and one of them was anti-Markovnikov, right? Our oxymercuration reaction was which one? Markovnikov goes on the more substituted carbon. Whereas our hydroboronation reaction was anti-Markovnikov. Goes on the less substituted carbon. So given this particular alkyne here, where one of my carbons is di-substituted and one of them is mono-substituted, all right, I want everybody to take a second and predict our hydration products here, given that oxymercuration is again a Markovnikov reaction and our hydroboronation reaction is again an anti-Markovnikov reaction. All right, so for my oxymercuration reaction, where am I going to put my hydroxyl group, on the red or the blue carbon? The red carbon, my more substituted carbon. And in my hydroboronation reaction, where am I going to put my hydroxyl group, on the red or the blue carbon? On the blue carbon, the less substituted carbon. All right, so given what we had learned about these hydration reactions with alkenes, this is what we would expect to be our product in our hydration reaction of alkynes. So first of all, these things right here, these are called enols. All right, why are they called enols? What does the ene mean? The carbon-carbon double bond, like an alkene, an ene. And what's the ol? Our alcohol group. So an enol. We have our carbon-carbon double bond located right next to our alcohol group, an enol. All right. These enols here, this is what is formed in this reaction. This is true. I haven't lied to you or anything like that. It is a little bit more complicated than this because it turns out that these enols are not stable. So these enols, although they are formed in this chemical reaction, they are not isolated. This thing is going to go on and to react to form what is our actual product in this reaction here. All right, and that's true for both of these cases here, regardless of whether it is the more or less substituted carbon. Our enol product is not isolated in this reaction. All right, so then what the heck is our product here? Okay, in order to figure this out, we got to talk about what enols are in equilibrium with. All right, and so this is our what's called a keto enol tautomerization. All right, which is a big scary word here, tautomerization. What is a tautomerization? All right, this is an internal rearrangement of atoms. All right, so if we take an enol here, turns out that this thing is in equilibrium with itself. I'm not reacting this with any other molecule here. All right, but this thing will rearrange itself to form a ketone. In this case, a ketone. Ketone or aldehyde, although we do always call it a keto-enol tautomerization. All right, and as we can see by our little equilibrium arrows here, this equilibrium very much so favors the ketone form. It's kind of one special case where that's not true, but we'll stick to the 99.9% of the time here. So our enol here is going to rearrange itself to form our ketone. All right. Now, I've said that this is the exact same, this is an internal rearrangement, meaning that these both have the exact same chemical formula. So I want you to take a second and figure out what bonds we're going to need to break over here and what bonds we're going to need to form over here in order to create our product. All right, we're going to be doing our mechanism. This is always a good first step for our mechanisms, figuring out what you need to be doing in your mechanism, what bonds need to be broken, what new bonds need to be formed. All right, the breaking one is fairly straightforward. What bonds do I need to break? Oxygen-hydrogen bond. What else? The carbon-carbon double bond. What bonds do I need to form on my product side? That oxygen-carbon double bond. And there's one more. All right, so if we look here carefully, over here, how many hydrogens are there on this carbon? Just 2. Over here, how many hydrogens are there on this carbon? 3. So that's our extra bond that we're going to have to form in this reaction here, right? Remember to fill in with your mind's eye those implied hydrogens. Notice that that is where our hydrogen in our chemical formula, like I said, they have the same chemical formulas, right? So in this tautomerization here, our hydrogen is jumping over to this carbon. All right, so we're going to do our reaction mechanism here. And this is a reaction that can be catalyzed in either acidic or basic conditions. All right, so in organic chemistry, we are often using acids and bases to catalyze our reactions. All right, and depending on those conditions, it lets us know what our mechanisms should look like here. So our reaction mechanisms, if they take place under acidic conditions, that means we have a lot of acid present, right? Which means that we shouldn't have any strong bases present. Strong bases would not be able to survive under acidic conditions. Okay, and we talked about how we can qualitatively assess whether we have a strong base back in chapter 3, or I guess chapter 2. All right, but a good sort of point to look out for, an easy thing to look out for, to make sure we have no strong bases is no negatively charged intermediates. And this is kind of a rough way of doing it, but it's a good thing to keep in mind. We can note there are some exceptions. Our halide ions are absolutely terrible bases. So even though they have a negative charge, they could exist under acidic conditions. Our hydrogen sulfate, right, our conjugate bases of our very strong acids, they're fine because they themselves are crappy bases. But nonetheless, with except for these few exceptions here, we shouldn't have any negatively charged intermediates. No negatively charged oxygens, for example. All right, so let's take our enol. Okay, we want to show our equilibrium here to our ketone. All right, we noted what what bonds we should be making and what bonds we should be breaking. Cool. And so we're going to do acidic conditions here. So let's add in some hydronium. Okay, so keeping in mind where we're starting and where we're going here, let's do our reaction mechanism. All right, that first step is we're going to look at these two here and try to figure out what our nucleophile is and what our electrophile is. All right, the electrophile in particular jumps out. Which one of these is going to be our electrophile? So first of all, nucleophile, electrophile, what's the difference here? Which one of those is electron rich? Which one of those is electron poor? I want everybody to take a second and think about this. We're looking for an electrophile. Are we looking for something electron rich or electron poor? We're looking for something electron poor for our electrophile, right? Something that wants electrons because it itself doesn't have any. So which one of these is our electrophile here? The hydronium. And what jumps out at us about the hydronium that makes us know it's electron poor? That positive charge, right? In particular, we said that acids are always electrophiles because what is our electrophilic site in an acid? That donatable proton. All right, so here's my electrophile. The rest of this here is going to play the role of what? The leaving group. Okay, and then over here, so this is my nucleophile. What's my nucleophilic site? And this, there would be two right answers. Two answers that are perfectly logical here. Because our nucleophiles are electron rich, right? So we got two electron rich sites here. What are the two of them? The carbon-carbon double bonds, and what else? Our oxygen with our lone pair. All right, now only one of these is going to be our nucleophile for this particular reaction. And what we want to do is kind of pay attention to where we're going here. If we do our oxygen as our nucleophile and we make another oxygen-hydrogen bond, are we any closer to our product here? No, right? So what we want to do is we said we wanted to break that carbon-carbon double bond. So then our carbon-carbon double bond here is going to be playing the role of our nucleophile. All right, nucleophiles attack electrophiles, and in this case, kicking off that leaving group there. So now everybody's going to take a second, give me the product following our electron pushing arrows here. Okay, so we have a new carbon-hydrogen bond here. We've kicked off that water leaving group. All right, what else is my intermediate missing? Carbocation, awesome. And our carbocation is going to go here. This is our more substituted carbon, but even more importantly is the fact that that oxygen's there. So we're just going to note that oxygen stabilizes that carbocation. And you can convince yourself that it can do so through resonance. All right, and in fact, that is our next step here, is we have one of our resonance patterns, an allylic lone pair. A carbocation adjacent to a lone pair here. All right, so everybody take a second. Given what we discussed about resonance patterns, what's our next step going to be? All right, why is that carbocation stabilized by that oxygen? Because of resonance, because that lone pair on that oxygen can come down to that carbocation. Okay, this forms a carbon-oxygen double bond, but importantly, I still have that hydrogen on there. So I have a positive formal charge on that oxygen. Remember, 1, 2, 3 bonds on our oxygen means we have a positive formal charge. But I'm close, right? I'm almost here at my ketone product. All right, I have one more step to go, which is to deprotonate this hydrogen here. All right, and what do we call our proton acceptors? Bases. All right, but here's the kicker, is we said we were under acidic conditions here. And all of a sudden, I'm under acidic conditions and I need a base. We said we weren't allowed to use any strong bases. So then what could I use as my base here to deprotonate my oxygen? The water. Awesome. So under acidic conditions, we're not allowed to have any strong bases. So our base that we're going to use is that weak base water. Right? And again, this is allowed because it's a weak base. Water, being both a weak acid and a weak base, can play that role. So then everybody, given that, take a second and finish this mechanism off, getting us to our product side. All right, we have a bond formation arrow and that bond breaking arrow to get us to our ketone product. Cool. All right, we're going to see a ton of reactions throughout this semester that are catalyzed under acidic conditions. And we're going to have this same common feature that we're going to see. And we're going to use this to make sure that our mechanisms that we propose make sense. That we should have no strong bases or no negatively charged intermediates in there. So if we do need a base under acidic conditions, we're going to have to use a weak base like our water. Okay, but this reaction in particular is great for illustrating these reaction conditions, because not only can we catalyze this reaction under acidic conditions, we can also catalyze the exact same reaction, our enol keto tautomerization, under basic conditions. I guess one more thing, if I'm going to be really good with finishing off this mechanism. What was the inorganic product of this last step? That hydronium. Notice how we reform that acid catalyst so that our hydronium is not actually consumed in our reaction here. What's up?
Can we have used the conjugate base?
In this case, the conjugate base was water, right?
But like if we use like sulfuric acid.
So sulfuric acid, it's not real. It depends on what's in the medium, basically. This is almost like never going to be your base because it's just the worst base in the history of anything. Anything else in that reaction mixture will likely play the role of the base. The sort of devil's in the details, but when we're talking about aqueous solutions, if there is something like a halide or a hydrogen sulfate present, yeah, you'll see it both ways, but what's more correct is to use what is the best base in that mixture, which is the water. All right, in this case, that was our conjugate base, but yeah. Okay, under basic conditions. So if under acidic conditions, we're not allowed to have any strong bases. Under basic conditions, what do we think the rule is? No strong acids. And we said code for no strong bases was no negatively charged intermediates. So what's going to be code for no strong acids? No positively charged intermediates. All right, and just to be clear, what would be a positively charged intermediate that I would not be allowed to have? If we look at that second to last step in our previous mechanism here, this positively charged intermediate is a strong acid, right? This hydrogen here is very easily donatable. So something like this will not appear under basic conditions. This is the exact type of thing that we're trying to avoid under our basic conditions. Okay, so now that we're under basic conditions, we're going to use hydroxide. All right, let's again try to identify our nucleophile and our electrophile. What jumps out here? A negative charge, which means that this is our what? This will be our nucleophile. Right? In my mind's eye, I can just see this oxygen glowing red hot because of that negative charge. It's got a ton of electron density. All right, well then what's our electrophilic site over here? That's kind of a tricky one. So a double bond plays the role of what? Nucleophile. It can't accept electrons. All right. Our oxygen plays the role of a nucleophile. It can't accept electrons. All right. So what we want to think of is we have this strong base here. Which one of our hydrogens is going to be the most acidic? It's not a great electrophile, don't get me wrong. But it's going to be our oxygen that is going to have that most donatable hydrogen here. All right, so this will be our electrophile. And what we have is just a simple acid-base reaction where that pair of electrons jumps onto that oxygen atom. Oh, that's not what I want to do. All right, so I have my alkoxide ion intermediate, and this is a great example of an intermediate that's perfectly legal under basic conditions, but that we would not be able to have under acidic conditions, right? This negatively charged oxygen here is a strong base, so it's okay under our basic conditions. It would not be okay under our acidic conditions. All right, so now again, we have one of our resonance patterns here. Now we have our allylic lone pair. All right, so everybody take a second. See if you can't remember our resonance patterns. What's going to be our other resonance contributor for that allylic lone pair? This is one of our this was our only resonance pattern that required those 2 electron pushing arrows. Okay, our lone pair can come down here, but we can't break that carbon's octet rule. So our pi bond has to jump up and become a lone pair on that carbon atom. So everybody take a second, follow these electron pushing arrows here. What's our product going to be? All right, I got my bond formation arrow. What am I missing? What's this bond breaking arrow doing? Yep, I need a lone pair on that carbon. All right, that carbanion. And then I'm almost there. Right, I'm almost at my ketone product. I got one more step to do. I need to add a hydrogen to that carbon. All right, so I need a proton donor or an acid, but we're under basic conditions, so I'm not allowed to use any strong acids. So what am I going to use as my acid? Again, water, and I guess we should have been good. We did produce water at that first step. So we have this proton donor floating around here. So then everybody take a second and finish this mechanism off. I guess our acid is that weak acid water. And we can notice that we produce our hydroxide ion, again, our basic catalyst. So again, that hydroxide ion was not consumed throughout the course of this reaction. Cool. All right, so all that to say that we have this keto-enol tautomerization that exists under acidic conditions. So the bottom line is when we do our oxymercuration or hydroboronation reaction, we're not going to isolate this enol product. Instead, we're going to get a different product. Given what we just discussed, everybody take a second and tell me what my product of this reaction will actually be. All right, so instead of getting an alcohol group in our products, we instead get that carbonyl group. So in my oxymercuration reaction, I have produced this ketone. after my keto-enol tautomerization. In my hydroboronation reaction, since I had this OH group on the end, I get an aldehyde as my product, again because of that tautomerization. All right, so our oxymercuration reactions and our hydroboronation reactions, they kind of do what we'd expect. We have that addition of water, but then there's this weird next step, our tautomerization, that will give us a carbonyl product instead of an alcohol product. All right, again, this internal rearrangement here to give us our carbonyl product. Cool. All right, so now we're going to talk about what we're going to call our synthesis strategies. Which is basically where we're going to take all these reactions that we learned and we're going to mix and match them. All right, and there's going to be one kind of key feedback loop that we're going to see here. Okay, if we take a carbon-carbon triple bond, we learned how we can convert that to a carbon-carbon double bond through those hydrogenation reactions. All right, and that's important because we learned a ton of different reactions for our alkenes, right? If we convert an alkyne into an alkene, we have all these alkene reactions that we could do. But we can also convert an alkene back into an alkyne. Which means that if we started with an alkene, we could make an alkyne, and then of course we learned a bunch of reactions that we could do with those alkynes. All right, but this kind of conversion back and forth here is going to be play a central role in our synthesis strategies. All right, so how do we do it? It turns out that you can treat an alkene with a halogen, like bromine. We already knew that. This produces this dihalide product, this product that has two of those halogens. If you take that product and you treat it with some strong base, and there are two that you'll see here, potassium hydroxide or even stronger sodium amide. This will actually convert that alkyl halide back, that dihalide specifically, back into an alkyne. All right, we're going to talk mechanism-wise about this reaction going forward. For right now, I'm just going to leave it as a reaction that we don't have a mechanism for. But importantly, we know how we can hydrogenate an alkyne to an alkene, but we can also convert using our halogenation followed by a strong base, an alkene into an alkyne. And this kind of conversion here is going to be important if we're going to be talking about what we're moving to next, which is what's called multi-step synthesis reactions. All right, so keeping this in mind here. Okay, so just to kind of show this pathway here, just to be clear, an alkene to an alkyne. Okay, so again, this will convert our alkene into that carbon-carbon triple bond, our alkyne. All right, that first step does exactly what we had learned in our previous chapter. Creates this halogenated product here. It is important that there's two halogens on there. All right, so this is a dihalide. Okay, and we can just note that what happens in this reaction is we're going to get rid of a halogen and a hydrogen, and we're going to repeat that process twice until we form our carbon-carbon triple bond. All right, so why is this going to be powerful here? All right, this is going to allow us to do some multi-step synthesis reactions. Okay, so I'm going to put two of these down, and I want you to work with your neighbors to try to figure out how you can go about completing the possible multi-step synthesis reactions. How can we convert our substrate into our product here? All right, in our first example, our substrate is going to be E2-butene. How do we convert that to Z2-butene? Or let's take our E2-butene and convert it into a ketone. Okay, so these are both conversions here that you're going to need to use not just one reaction, but you're going to have to string together a few reactions in order to do it. I want everybody to try to take a second and see if you can't figure out how to do our multi-step synthesis here. I want you to work with your neighbors, check your work, see if you can't both figure it out together, et cetera, et cetera. All right, so how are we going to do it? How are we going to convert our E to our Z? There's no way to switch stereochemistry that we learned for our alkenes. All right, but importantly, we did learn about this stereospecific hydrogenation method for our alkynes. Right? We can convert an alkyne into a Z alkene here using Lindlar's catalyst. But we have to start with an alkyne in order to do it. So in our multi-step synthesis pathway, what are we going to do? We're going to first convert our alkene into an alkyne by using that halogenation reaction. I'm not going to worry about stereochemistry here because it's going to get ruined in that next step. All right, so we can just ignore stereochemistry for this particular one. This gives me my dihalide. And then as we said, I'm going to put just one of those bases here. That would convert this to a carbon-carbon triple bond. Then we got one more step to go here, so that would be step 2. Step 3, we would then use that H2 and Lindlar's catalyst in order to convert our alkyne into that stereospecific Z alkene. All right, what if we wanted to convert into a ketone here? Let me shrink this, make some room. We actually do have a way to make carbonyls from our directly from alkenes, but those are those oxidative cleavage reactions. That would give me an only 2 carbon, and in that case aldehyde, not even a ketone. So I don't want to lose any carbons in this process. All right, but what other reactions do we have to create carbonyl groups? All right, what did we learn earlier today? Our hydration reactions of alkynes will produce ketones or aldehydes. All right, but I have to start with an alkyne in order to do it. So again, key here to our synthesis strategies, we can again do our halogenation followed by our strong base. For the sake of variety, I'm going to use a different strong base. I could use either. Okay, this will give me that alkyne. All right, and then I'm going to need to do a hydration reaction. In this case, they are both secondary carbons, so it wouldn't really matter which one I chose. I'm just going to do I think what would practically be cheaper, my mercury sulfate, water, and sulfuric acid. Although if you said instead a hydroboronation reaction, that would work perfectly fine as well. Right, but we're going to need to then create our enol intermediate that'll then tautomerize to our ketone product. Sorry, that's a 2. Okay, so we're going to start putting these reactions that we learned together to create this multi-step synthesis pathway. There's one more reaction that we're going to learn, and this one's probably going to be one of the more powerful ones that we've learned thus far. And that is to convert terminal alkynes into carbon nucleophiles. Carbon is not an atom that we associate with being a good nucleophile because it doesn't have those electron pairs, those lone pairs. All right, but it turns out that we can convert a terminal alkyne into a carbon nucleophile because, importantly, a terminal alkyne has this hydrogen on the end here. Right? By definition, that fourth bond, if it's on the end, has to be a hydrogen. Okay. So why is this going to work here? Let's rewind back to our discussion of acids and bases. All right, if we're talking about carbon, this is our pKa table here. We're going to have to go all the way to the very end of our pKa table. Because remember, carbons hold on to their hydrogens very strongly. All right? If we look at that very last entry on our pKa table, this is our sp3 hybridized carbons. pKa's of 60 and above, which is basically a way of saying you're never going to ever be able to deprotonate an alkane. Right? You can't get that hydrogen off of there. There's just no base strong enough to do it. All right, but we talked about how the orbital, sp versus sp2 versus sp3, matters. If we go to an sp2 hybridized orbital, it's a little bit less of a pKa, but still very, very high. All right, but if we get to our sp hybridized orbital here, now our pKa is 25, which is still like an absurdly high pKa, don't get me wrong. But there are some bases out there, specifically the conjugate base of this, our sodium amide, would be strong enough to deprotonate an alkyne. All right, and so that's exactly what we're going to do. We're going to take our alkyne, we're going to add in some sodium amide here. But importantly, the sodium is just a counter ion. So I'm going to erase that and replace it with a negative charge. And this thing here is just a super strong base. Strong enough that it can deprotonate this really crappy acid here, our terminal alkyne. All right, and so that super strong base steals that proton, creating our carbanion nucleophile. Oh my God. All right, now we have a lone pair and a negative charge on that molecule. All right, so then why is this so powerful? Because this is step 1 in our process. Step 2, we're going to take that carbon nucleophile and we're going to react it with an electrophile, like an alkyl halide. All right, in this electrophile here, what's my electrophilic site? Is it the bromine? No, bromine's the more electronegative one, pulling electron density away from that carbon. The bromine is what in this molecule? The leaving group. All right, so our good carbon nucleophile is going to attack our electrophile. Everybody take a second and draw me my products here. All right, yes, we get a bromide ion. That's not going to be very important. All right, and make sure to count carbons. It's kind of easy to lose track of your carbons. All right, so what I'm going to do is color my 3 carbons in my nucleophile in red here. All right, so I'm going to start by drawing those same 3 carbons. This one on the end here was my nucleophilic site, so I'm going to highlight that as well. And I'm going to draw my new carbon-carbon bond. I'm going to be good and put it linear here. Then what lives on the other side, it must be my electrophilic carbon. This one here. My electrophile also had that additional carbon. All right, so I should have a total of 1, 2, 3, 4, 5 carbons on the left. So 1, 2, 3, 4, 5 carbons on the right. All right. And importantly here, the big difference, and this is what we have not seen yet in this course, and what we'll actually see fairly rarely throughout the course of these 2 semesters, is what we have here is a way of creating a new carbon-carbon bond. Right? Everything else we've been doing is like swapping one functional group for another here. Now we've actually made a larger molecule than what we started with here, right? We join these 2 fragments together, and that's what's going to make this so powerful, is we have a way of creating this new carbon-carbon bond starting with our terminal alkyne here. All right, so where we're going to end, the last 2 that I want you to work on, again, multi-step synthesis here. You're going to work on doing the following 2 conversions. We'll leave it at that. Cool. definitely. So it's not a bad idea to kind of like work from both ends here. So yeah, so you know you're gonna have that to get here for. You are missing one more thing.
Yeah, I'm going to, so that's not the
Remember to actually make it longer, you're gonna add.
Because you're gonna make the.
No, we need to do the strong base, the convert terminal alkynes and
Oh, it's a terminal, right?
Yep.
yeah.
The triple bond. Oh, your enol? You don't have to draw your enol because that's not actually something that's like an isolated product.
Okay, so it is.
That's yeah. I mean, to be good, if you have like water and sulfuric acid.
Okay.
Yeah. That's what you want to do. Just treat that with that too. Yep. Cool. All right, so y'all will have a lot of practice. One thing I just want to be super clear on here is we did these hydration reactions here and we showed these enol intermediates. All right, this was just to sort of show how we have our normal hydration reaction, but then we have this weird rearrangement to get to our product. You wouldn't have to show that enol. In fact, we can kind of summarize these reactions up maybe a little bit better by just showing what our end product is here, right? When you treat an alkyne with that mercury sulfate, water, and sulfuric acid, you get a ketone product. You don't isolate that enol, right? That was the whole point, was that this isn't what is formed here. Rather, it's formed, it just quickly falls apart into this thing here. Same thing over here. If we're going to summarize our hydroboronation reaction, let's just grab our reactant and our final product here. No. Okay, so yes, you have that enol intermediate, but importantly, these are ways of converting alkynes into aldehydes and ketones. Oh, I get it. All right, so this is kind of our summarized chemical equations here. We showed those enol intermediates to show that we do have our normal hydration reaction, but then we went on that long spiel about that tautomerization to produce our ketone or aldehyde product here. Cool. We'll leave this up just in case anybody needs